let's look at some familiar surfaces. Okay, now the torus, as you all presumably know, because it's the circle cross circle, and the circle is an interval divided by with the endpoints identified, can be written as a square with sides being identified this way. I have alpha again, and then I have beta, maybe two arrows to distinguish, and then beta. Okay, so this is actually a 2 complex. So this is a 2 complex, and the above picture shows it a bit better. You have a vertex, but that vertex is here, and I have 2 edges. So one 0 cell, 2 edges, or 2 1 cells, and one 2 cell, which is attached according to this picture, this reason. So we just took this and attached according to the map, which is given by the boundary being alpha, beta, alpha bar and beta bar, and we ended up with the torus. Okay, so by definition, so that will tell you that pi 1 of the torus with x0, which we knew also because it's a product, but is going to be given by alpha and beta, and with the relation that the boundary alpha bar is 1. Okay, so this is often written alpha beta semicolon alpha bar beta bar equals 1 for readability. The formally equals 1 is redundant, but you can also write it as alpha beta equals beta alpha. That is generators that commute, and this is isomorphic to z squared. How about a more complicated surface? So let's take a picture here. This is the 2 torus, 2-hole torus or something, surface of genus 2. Well, I can break it along this curve and view it as a torus and another torus glued together after removing disks from both of these. So this is called a connected sum operation. Okay, so let's look at what this is. So let's take 2 tori, and I'm going to call this side alpha 1, beta 1, and again we have alpha 1, but the other direction, and again we have beta 1. So along the counterclockwise, it's alpha 1 bar and beta 1 bar, and we similarly have tori like this. Okay, so what happens to this guy? Well, this is alpha 2, this is beta 2, this is alpha 2 bar, but since I changed the arrow, I can call it just alpha 2 beta 2 bar. Now we are supposed to be deleting disks from that. So let's delete a disk at the vertex like this and like this. Okay, and so now let's look at some calculation here. Surface of genus 2. So let's see what this creature is. So we have a square and we deleted. So we have this way 2 lines, single line and 2 lines. Okay, and we delete this. Well, this is the same as if I took, let me use a different color for the deleted guy just to make it more vivid. This I claim is the same as taking a line like this. Maybe we'll even make it longer, like this, and having our edges as alpha, beta, alpha bar, and beta bar. Okay, so single line, double line, single line, double line, and for clarity, let's use the term alpha 1, beta 1, alpha 1, beta 1 in this direction. Why is this? Well, by transitivity, this vertex is the initial point of alpha 1. So it is identified with the initial point of alpha 1 here, which is the terminal point of beta 1, which is identified with the terminal point of beta 1, which is the terminal point of alpha 1, and hence identified with this. Okay, and so terminal point of alpha 1, and finally that's the initial point of beta 1, and so it's identified with this initial point. So we started with this vertex and we saw it was identified with all the other vertices just by the identification of sides. That means these two are actually identified. So this picture is actually equal to this. So that's wonderful, because that means that if I took another copy, okay, here, let's take another copy here, okay, and let's, for emphasis, call this alpha 1, beta 1, alpha 2, beta 2. And here we have alpha 1, beta 1 again, and not alpha 2, beta 2. And here we had alpha 2, beta 2, and we had alpha 2 and beta 2. But since we're going to mix them up, let's put some different notation. Put a dashed line before these arrows to clarify what we have. Well, let's send this guy here. Okay, just for fun, but by this guy I mean we'll delete a little bit here. Okay, so then that picture can be viewed as taking a line like this. Okay, I just turned it upside down, and then I would get with alpha 2 and beta 2. So sorry, I have to correct the arrows, and alpha 2 and beta 2. This time alpha 2 came in the other direction, and beta 2 came in the other direction, beta 2. And these two are identified with each other because that's what we have done. We have glued these two together. Okay, so this surface with this identification is simply an octagon and as we go along the sides we get the word which is going to be alpha 1, beta 1. Now instead of arrows, let's write it down. So I'll write it as alpha 1 bar, beta 1 bar, with the understanding that we are always clockwise. And here we have alpha 2, beta 2, alpha 2 bar, and beta 2 bar. And we can repeat this, because if I do the same connected sum operation again, remove one more disk and then attach this guy here, I get a surface of genus 3. So this means that if I take a surface of genus G, okay, I have drawn 3 here, it's a 2 complex. So genus G, this gives you a 2 complex, and the 2 complex is going to be having alpha 1, beta 1, then alpha 1 bar, beta 1 bar, etc. And finally it's going to end with beta G bar. Okay, just before that there will be an alpha G bar, etc. Okay, and thus if I take this surface of genus G, we'll call it sigma G. The word sigma is used for surface because S will sound like a sphere. Thus pi 1 of sigma G with whatever base point you want, x0, is going to have the following presentation: alpha 1, beta 1, and so on up to alpha G, beta G. Okay, and just one relation which says product I equals 1 to G of alpha G, beta G. Let me write it as a commutator, where we recall that the commutator of xy is the expression xy, x bar, y bar, or if you prefer in a group xy, x inverse, y inverse. So where does that leave us? Pi 1 of xg, x0 is this. So this is nice. We know the fundamental group of all the surfaces, at least the closed ones. Now if we have a boundary, it's as if we punctured here, then we can deformation retract onto the boundary. So you actually get a 1 complex. And if we puncture in 2 places, you can see that we can maybe add a loop like this, and you'll deformation retract onto the union of the boundary and this loop. So you get, if it's a punctured surface, you get a 1 complex, and the rest of the oriented surfaces are 2 complexes. Okay, and let us just record as our last example of 2 complexes before we turn to the final videos in this segment of the course, which are a topological proof of Grushko's theorem. So let's record here at the 2 complexes the theorem that sigma G equals sigma G prime implies G equals G prime. This is not so obvious. Indeed, if you are given two presentations of groups, there is no algorithm to tell whether they are the same or not. It's algorithmically unsolvable. Okay. However, in this case, what you can do is you can abelianize. Okay. So, namely, given a group G, so if G is a group, we look at the abelian group GG. This is the normal subgroup generated by GH, G inverse, H inverse with G and H in G. Okay, so normal subgroup generated by this set. Okay, and so G over GG is abelian. Now what happens when you abelianize here? Now if I look at pi 1 of sigma G x0 abelianized, that is I divide it by the commutator subgroup, as it's called, of sigma G x0 with itself. What happens to this guy? What happens to the relation? Well, it just dies, you see, because for example, if I took, so if I look at alpha G, beta G, this is equal to identity in G over GG. Each one of them, and hence their product is the identity. So this just makes it, so the relation disappears, so we end up with just the free group divided by its commutators. So this is the free group on 2G generators divided by the commutator and the free group on 2G generators, which is Z to the 2G. Now by the structure of abelian groups, you know that 2G, the rank of a free group, free abelian group, is determined by the group up to isomorphism. Or if you wish, you can tensor with R, say, or Q and make it a vector space and use the dimension of the vector space. Okay, so with this we have seen how we can calculate fundamental groups. Every space is, every group is the fundamental group of some space. And these were just a couple of examples, but in many, many cases, we can do a combination of these things. We can express them as two complexes, or we can decompose and use Van Kampen's theorem. The big difficulty, on the other hand, is what we get is often a presentation of a group, and as I said, basic questions are unsolvable. That's a whole different story. Okay. So with this, we'll leave this core part of the course, except to see some interesting applications to group theory.